Hello and welcome to the EMC Live webinar, Improving EMI Compliance and Pre-Compliance Testing, Throughput with Time Domain Scanning. My name is Belinda Stashukevich and I'm editor of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Mark Terrian. Mark is a business development engineer at Keysight Technologies. He has over 20 years of product development experience with HP and Keysight, formerly Agilent Technologies, with a focus on EMC receivers, spectrum analyzers, and microwave test equipment. This webinar is sponsored by our silver sponsor, Keysight Technologies. Keysight is the world's leading electronic measurement company, transforming today's measurement experience through innovations in wireless, modular, and software solutions. With its HP and Agilent legacy, Keysight delivers solutions in wireless communications, aerospace and defense, and semiconductor markets with world-class platforms, software, and consistent measurement science. The company's 9,500 employees serve countries and customers in more than 100 countries. This webinar is one of many. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You'll be able to ask questions and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Mark will begin the presentation.
Good morning, everyone. Welcome to my presentation. Thank you very much for attending. Today we're going to talk about how you can improve your EMC compliance and pre-compliance testing using a new technology. It's called time domain scanning. For an agenda today, I will spend some time, first of all, talking about what is time domain scanning. We'll go over the basics of it, how it saves time, and we'll talk about the other benefits associated with this technology. And after we go through that, we'll spend some time talking about some of the issues and concerns that have come up around using time domain technology, and talk about how it interacts well with both the standards as well as the receiver, the spectrum analyzer design. So the whole focus of being able to speed up EMC testing is to help either your revenue and or your time to market. If you are a EMC test facility, time is money basically. Compliance testing is the focus of your business, and usually chamber time is the limited resource. If you're a manufacturer, a lot of the situation is the same. The chamber time is typically the limited resource. So what you're going to want to be able to do if you're doing pre-compliance testing is get your products in, get them tested, and then move on as quickly as possible. So anything you can do to reduce your test time improves your efficiency and your profitability. If you're pre-compliance testing, the ability to rapidly troubleshoot and diagnose your device under test quickly is also very important. The sooner you can test it, the sooner you can do your diagnostics on it, the sooner you can either make changes to it or determine that you're finished with your design and able to move into the final compliance stage. So time domain technology is one of the tools available in the market today to really help speed up your testing. Let's look at the factors that affect EMC test time. First off, there's the device under test setup time. This can vary depending upon what you have. If you have a fairly small device, you could very easily carry it into the chamber and set it up in half an hour, 30 minutes, or 45 minutes, something like that. If you have a larger device, it may take you several days to set the product up. So there, the time there is strongly a function of what it is that you're trying to test. You don't have much control of that. Another key aspect to collecting data is the receiver and spectrum analyzer scan times. Scan times in some ways are limited or stated by the specific standards you're testing to, so you're only able to move so quickly. Scan times can be a major portion of the time taken to do the testing. Third element is the turntable and antenna movement times. If you're measuring to a CISPR or to an ANSI standard, you need to rotate your turntable and move your antennas to maximize the signal that you've seen. Typically, it can take on the order of 15 to 20 minutes total of turntable and antenna moving time during a typical CISPR type test. So that element of the time is fairly well fixed in that time frame, depending upon which turntable you have and the speed of your antenna motors. Then after you've collected all your data, you have to do your suspect frequency analysis. Again, the time associated with this is a function of how many frequencies you have on your list. If your device is clean and you pass all your signals, obviously you don't need to spend any time in this area. If you've got hundreds of signals you want to investigate, again, that's going to take time for each one of those. But again, this is an area that's strongly a function of your design and the device under test. And of course, the final measurement. The final measurement dwell times are specified in some cases depending upon the standard that you're using. So this time is also a function of the measurement time and the number of frequencies you need to test. So the main focus area that we can have as equipment providers for customers is to how can we make our receiver and spectrum analyzer scan times quicker. This is where time domain scanning comes in. So what is time domain scanning? It's a new way to do frequency scanning. Receivers in the past have either swept or stepped or have done either, your choice. Now we have this new capability called time domain scanning. Time domain scanning is FFT based. It looks over very broad frequency spans and uses up to a 90% or so overlap in time to ensure that we've got the amplitude accuracy for the measurements that are required by CISPR, ANSI, and by MIL standard 461. This technology became prevalent in 2010 in CISPR 16, where this type of measurement technology was allowed for parts of the measurement, but certainly not required. There are certain industries have adopted this more than others. What we've seen is that the automotive industry has adopted this for a lot of their internal standards. So the main benefit, again, is to reduce time. It helps you collect your suspect frequencies faster. The benefits, those testing to those standards that require a lot of scans for, especially those that require turntable and antenna optimization. I'll give you an example of this in a few slides. So how does time domain scanning save time? Let's look first on the left side of the display on a more traditional measurement methodology where you're using swept or stepped frequency scan. The standards you're particularly testing to have dwell times or measurement times associated with each measurement you make. For example, MIL standard requires 15 milliseconds of dwell time per scan, say if you're measuring in the 30 megahertz to 1 gigahertz range. CISPR's dwell times are a function of the device you're testing. You need to look at the slowest pulse repetition frequency you have in your device and set your dwell times to equal 1 over that. So if you have fairly low pulse repetition frequencies for your device under test, you may have to set it to several hundred milliseconds per scan. And for swept or stepped scans, you need to dwell this a selected amount of time for each resolution bandwidth worth of data you collect. If we go look at the time domain scan now, what time domain does is collects information in a much broader frequency span. For example, if you look at commercially available receivers today, they could be in the 10 to 40 megahertz worth of bandwidth data at the time. So let's assume 10 megahertz for a second, and let's say you're measuring to the CISPR band C and D with a 120 kilohertz resolution bandwidth. You're going to be, in each 10 megahertz collection, you're going to be gathering roughly 100 resolution bandwidths worth of data. The time saving comes in that you only need to dwell for the FFT bandwidth, not for each of the resolution bandwidths that you collect. So that's the time savings in the data collection. So to understand modern receiver architecture and some of the benefits of driving the time domain collection capability, let's spend just a couple of minutes talking about classic receiver or classic spectrum analyzer architecture. Initially, you have an RF section where your signals come in from the left in the input and run through a level of attenuation and typically pre-selection if you're looking at a receiver, and then run into the RF down conversion stage. The RF down conversion stage takes the input signals, mixes them with the local oscillator or the synthesized signal generated inside the machine, and uses it to generate to mix down or down convert, depending which language you want to use, to the IF where more analysis can take place. The IF frequencies tend to be very narrow band, typically designed around a single frequency. So your RF section may cover, say, 10 hertz to 40 gigahertz, and your IF stage at this point will be in the hundreds of megahertz range. At this point, you've got your resolution bandwidth filters, which allow you to do different types of analysis on the signal. You have your IF gain stages, which are selectable in order to bring your signal farther up on the screen. As you recall, looking at spectrum analyzer, the reference level is typically called the top gradical of the display. And typically what people like to do is bring their signals up closer to the higher signals, especially in older analog machines where the accuracy is the best near the top of the screen. And of course, you want to have significant dynamic range. As you look at the signal, you want to be able to look over, many tens of dBs. So the signals, once they've been processed by the IF gain, they come through the log amplifier. And that provides 70, 80, 90 dB of usable display range on your screen. Then after that, the signal was detected, typically with a peak detector, but there are certainly other types of detectors that are available in spectrum analyzers and receivers. What facilitated the oncoming of time domain scanning is the availability of what we call an all-digital IF architecture. In modern receivers and spectrum analyzers, if you look at this area here, what used to be the analog circuitry associated with all the IF circuits I just mentioned, that is now all being done up in DSP. So we're sampling at a much higher frequency here. We have much better A to Ds than we did years ago. We're able to sample at much higher frequencies, collect the data, and be able to do all the processing in software. So having this capability with the wider IF bandwidths, the more powerful processors, and a lot of the advanced DSP techniques we have today, we're able to have a very powerful time domain scanning capability in the receivers. So let's look at the CISPR radiated measurement methodology. This is a methodology recommended by CISPR, and see where time domain technology really helps. First area is recommended to do a fast pre-scan to collect all your suspect frequencies. These are typically done with a peak detector. The point here again is, CISPR knows that we want to keep our accuracy but also minimize our test time, find the right balance there. So the focus is, let's find the signals of the peak detector that are over the limit. Once we have that, we can collect, once we have what's called our suspect list, we can then go ahead and perform final measurements on the individual signals that are actually over the limit once we've done an analysis on them. And it's this upper area here where we're doing our fast pre-scan where time domain scanning really helps. Let's look at an example of that. Let's say we're making a measurement on a device, again, a CISPR-based because of the tower and turntable optimization requirements force the users to make a lot of scans. So typically you have a device under test on the turntable that's a specified distance away from your antenna under test. And according to CISPR, you're supposed to rotate this device to 360 degrees, scanning at every 15 degrees at a minimum. So that gives you 24 scans right there. And then you need to move your test antenna up and down to try and identify the maximum of the signal that you see. Let's say for this example that you would make a measurement at 1 meter, 4 meters, and then 1 in the middle. So that's 24 times 3 additional scans, because at each time you need to do a rotation. And then we have both vertical and horizontal polarization. So you're going to make 144 scans when doing this characterization on the device. So let's look at what's available in the technology today from a frequency domain scan time. Using the assumptions that we have on the left here, for example, if you want to measure in CISPR band CD, which is 30 megahertz to gigahertz, using a peak detector, and let's say a 10 millisecond dwell time, which would be a typical dwell time used for the measurement. If you look at the industry today, for the spectrum analyzers or the receivers that are available, be they ours, be they our competitors, you're going to see that the industry is going to sweep on the order of 250 seconds, so roughly 4 minutes to do one scan. So if you just multiply that through, you're going to take over 10 hours to collect the data. Again, this is just the data collection. Now let's look at how time domain scan can help this. Assuming the same conditions that I've shown here for CISPR band CD, if you look across the industry to see what's available, you'll find time domain scan times on the order of a half a second to 13 seconds to cover the same scan frequency range versus 250 seconds for frequency domain scan. So that's a significant time savings there. So if we come through and apply that to the same CISPR methodology that I was discussing earlier, you're going to take that 10-hour scan time down to about 5 minutes, assuming in this case 2-second scan, which is roughly average in the industry. So that's the benefit to your time save, the benefit to you for EMC testing. Another benefit for time domain scanning comes when you've got devices that can't operate for long periods of time for a variety of reasons, be they thermal, which is typically the case, or there's some other elements which limit the amount of time the device can operate. One example would be automotive starter motors. You know, starter motors have gotten smaller and smaller over the years. They can't be operated for multiple minutes in order to create a scan on them. So what automotive industry has done is gone to using more time domain collection techniques to allow them to shorten the test time of the device so they don't have to stress the device beyond its design limits. Let's focus now on MIL standard 461. MIL standard requires a lot fewer scans than a CISPR or an ANSI test does because there's no turntable rotation and there's no antenna motion. But MIL standard does specify specific dwell times for swept or stepped scans. MIL standard 461F is several years old now and really didn't mention time domain scanning because the technology wasn't available the last time MIL standard 461F was revised. There is a new version of MIL standard 461 called 461G. There's a proposed draft out for industry review right now. It just came out last month, and this draft is taken into account this newer technology and has made a statement about how it can actually be used. Here's a copy of what's called Table 2 of the document, if you're not familiar with it. This specifies the frequency range of the tests that needs to be done, the 6 dB resolution bandwidth that you need to use to make those tests. Again, roughly analogous, if you're more familiar with commercial testing, to what CISPR or ANSI have. If you have a stepped or swept tune receiver, this third column and the fifth column would be the times you would need to adhere to if you're going to make your test. And here's the new column here where they specifically call out FFT receivers and specified dwell times for each of the acquisition bandwidths that's collected. And so it's a little different than what CISPR offers, in that CISPR says you need to set your measurement time based on what your device does. This comes through and says, here's the dwell time that you shall use. But with this, the improvement is still significant in terms of time savings and trying to cover the frequency range mentioned here. So that was the overview of time domain scanning. Let's go in and talk about some of the issues and the concerns associated with people that have used time domain technology. First off is making sure that you set your dwell time correctly. Let's look at the upper display that I have here. We're looking at a pulse signal, a period of 20 milliseconds with a 2 microsecond pulse duration itself. And I'm dwelling and collecting information every 20 milliseconds. So my dwell time, my measurement time, is equal to the pulse period time. What we'll see on a time domain display would be the expected display of the signal. It's a sin x over x type of display here, showing all the frequency components of the impulse. This is a 500 megahertz pulsed RF signal. What happens if I set my dwell time less than the pulse period? What we'll see down here in the bottom, I have the same pulse duration, but we'll see that during some of the collection times, pulses, I'm not actually seeing one of the pulses that exist. What does that look like on the receiver or the spectrum analyzer display? Well, it looks like in some sections of the frequency here, frequency range, we're not displaying any data. So this is why it's so important to understand what your device under test is and be able to set your dwell time correctly. With the mill standard, by setting the times the way they have, they've identified ranges that are comfortable for mill standard 461 to be able to collect be able to sample the data correctly when they're using time domain scan. Another aspect of using time domain scan is being able to comply with CISPR requirements. So CISPR 16-1-1 2010 version, which is the document which describes what an allowable CISPR receiver is, it states that you can use time domain scanning as one of the technologies for collecting information. So this is a very key contribution and an enhancement to the industry. Is it usable for final measurement? Currently, time domain scanning is only usable for final measurement if the specific standard you're testing to references that version of the CISPR 16 document. Currently, only CISPR 13 and CISPR 32 reference the 2010 document, but the other CISPR documents are being adapted to that. I'm on one of the CISPR committees involved mostly with CISPR 16, but I know my compatriots are also working on updates to the other CISPR documents in order to be able to adopt time domain technology. But there's another element to this too, that the methodology has to comply with the recommended measurement methodologies given in some of the other CISPR documents. For example, CISPR 16-2-3 talks about, it addresses how to make radiated emissions measurements. And in there they call out specifically, they have to monitor each of the suspect signals that you've collected during your suspect scan to determine whether the quasi-peak value is constant or not. If the quasi-peak value isn't constant, the user is supposed to monitor that level for up to 15 seconds in order to be able to capture the variation. And if the variation is more than plus or minus 2 dB in that 15 seconds, the signal needs to be monitored for a longer time, unspecified in the CISPR document, to try and capture the peak signal. So unfortunately, just doing a single time domain sweep across the scan with a quasi-peak detector, which should be significantly faster than using frequency scan with a quasi-peak detector, unfortunately, that doesn't meet the requirements of the CISPR in order to make this type of measurement. So when using time domain, again, that's why we say that the most benefit that time domain scan offers is to your suspect list collection. So there's another issue when you look at your receiver design that you need to take into account for time when considering a time domain measurement, and that is the whole concept of preselector receiver overload versus time domain speed. The time domain speed is a function of the width of the acquisition bandwidth that you can collect in your IF and the processing speed of the receiver, but it's also the acquisition bandwidth that you have is limited by your RF preselection bandwidth. Let's look at that in a little more detail. Before we go into that, I need to spend a little time talking about what is an RF preselector and why are we using it. I'm going to start with a simplified block diagram of a traditional spectrum analyzer. Most spectrum analyzers today that cover into the higher microwave regions are broken typically into two paths. There's usually a low band path, which in our machines are 3.6 gigahertz, but other manufacturers use different switchover points, and the high band path. The main difference between these two is the way that the design of the preselector is done to ensure that you've got image-free displays on your screen. In a low-pass filter, in the low-pass band path, typically what designers do is they move the mixed frequency to a higher frequency, and then they use the low-pass filter here to make sure that all the images from the down conversion are moved out of band, and that you're only going to be able to view signals that you're going to be able to view the signal that you're looking at, not at an image. In the high band path, because the technology is more difficult to do covering the broader microwave regions, what most manufacturers do is they use a very narrow YIG preselector in front of the mixer to limit the energy that comes into the mixer and goes through the IF. So again, you're only looking at the signal of interest and not at an image of the signal. If we switch over to an EMI receiver now, EMI receivers tend to add something called an RF preselector to this in place of that bandpass, in addition to that bandpass filter that I mentioned earlier. So what is an RF filter? It's a bank of filters before the first mixer, and the benefit to this is that it provides, it removes a lot of the broadband impulsive energy that can come through the front end of a spectrum analyzer to the low band down conversion chain, which improves the impulsive dynamic range of the measurement. So if we look at this, and if we have this preselector, which is a range of filters in front of the down converter, the wider the preselector filter I can have, the wider the acquisition bandwidth I can have to collect data through that filter. The fewer acquisitions I have means the faster I can cover the whole frequency range. So that would give me fast data collection. But the problem is this, in that these wider preselector filters open up the front end of the receiver for overload. So let's look at the physics of it. If I've got a pulse of amplitude V sub P and pulse width T, if I've got the pulse coming into my receiver, the voltage that passes through the preselector filter is proportional to the amplitude of the pulse, the width of the pulse, and something that's called the impulse bandwidth of the receiver. The impulse bandwidth is nominally the 6 dB bandwidth for a Gaussian type filter, which is what most people use in their RF preselectors. So because of this, the wider the impulse bandwidth of the preselector, the greater the voltage that's going to come into the mixer. So what we're seeing then is if you have a receiver that has wider preselector filters versus narrower preselector filters measuring the same signal, the preselector with the wider filters would have the opportunity to overload earlier than the filter with the narrower preselectors. So while this type of design may allow faster time domain scans, you also have to be a little more careful in the signals that you measure to make sure that you're not overloaded. So let's look at the situation where we are overloaded. Again, we've got two receivers measuring the same pulse. One receiver has the wide RF preselector filters. The other receiver has a narrow RF preselector filters. If we've got such a large pulse here that receiver 1 is overloaded, how do we get rid of the overload? We do that by adding RF input attenuation at this point. So once you add RF input attenuation to eliminate the overload, you've now reduced your sensitivity. Well, what is one of the key parameters for an EMI receiver? Sensitivity. So if you're trying to measure a range of signals in fairly wide dynamic range, and you have very wide preselector filters, you could be in a situation where you're overloading and you have to add more input attenuation, which will to make it more difficult to measure the low-level signals. Again, it all depends on the signal dynamics that you have. So the issue here in wrapping up is that time domain significantly reduces your test time. CISPR allows it, and it has the greatest value in pre-scan. Mill standard 461G is allowing it once it will be released, which will probably be later this year. If you're using time domain scan, it's critical to use appropriate dwell times to make sure that you're capturing pulsed information each time you do a time domain acquisition, and that when you're using your pre-selected receiver, you need to make sure that when you're doing your time domain scanning, that you are using it in a linear area, that the wider filters could give you the possibility of greater overload. So there are a variety of receivers in the market today that offer this capability. One that we offer is the N9038A. We have time domain capability with this as an option. So some people have adopted this technology and want it now. Some people are still considering it and may want to upgrade to that in the future. Our receiver allows you to do both capabilities of that. I've been talking about receivers, but this technology also applies for pre-compliance scanning, where you're going to want to use more of a spectrum analyzer than EMI receiver. A lot of that has to do with the cost of the receiver. The EMI receiver tends to be more expensive than what people want to use in a pre-compliance application. So my company offers a range of spectrum analyzers which have optional time domain scan capability built into them, utilizing with a specific application we call the N6141, which is the EMI user interface taken from the N9038 receiver and brought into the pre-compliance environment to help you collect the information. So with that, I'd like to thank you very much for your attention and hope I've been able to give you some information today, and wonder whether you have any questions.
Great, thank you so much, Mark. We'd like to have a call for final questions from our audience. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our websites, emclive2015.com or interferencetechnology.com. You can also email us with specific needs and we can direct you accordingly. Mark, here's a question for you. Could you describe again how time domain scanning reduces scan time?
Time domain scanning reduces scan time by allowing the user to collect much broader spans of information than the typical mill standard or CISPR bandwidth. then it allows the user to collect many bandwidths of information, but only needing to dwell or pause once for that collection versus traditional receiver where you'd have to do the dwell or measurement for each of the resolution bandwidths of the data collected.
Great. Here's another question. Does it matter whether pre-selector filters are fixed or tunable?
No, not at all. They could be tunable, they could be fixed. It really depends upon the design of that the manufacturer has chosen. The point is that you're reducing the bandwidth of the spectral energy that comes into the first mixer.
Great. We have another question. Is TDS compliant to CISPR 25 final measurements?
Not at this time. It's only 13 and 32.
Okay. Here's another question. Do different dwell times have to be used for time domain scanning versus a traditional step scan to achieve the same results?
You need to use the same dwell time that you would use if you were scanning frequency scan with time domain scanning. So again, the dwell time for commercial applications, the dwell time is a function of the pulse repetition frequency of your device under test. If you're doing frequency scanning, you need to make sure that that resolution bandwidth is parked long enough to be able to collect that sample of information. If you're using time domain scanning, you need to make sure the acquisition bandwidth is parked long enough to be able to collect one of the impulses that comes out. So the dwell time should be the same or longer than your pulse repetition frequency for both frequency scanning and TDS scanning.
Great. Per the industry standards, can time domain scanning be used for both preview measurements and final measurements?
They can be used for preview, when we're talking about commercial now, it can be used for preview scanning, but again, final measurements, the standard you're actually measuring to itself has to reference the CISPR document, the specific CISPR document that authorizes time domain scanning. And the ones that are available now are CISPR 13 standard and CISPR 32 standard. But the other ones are being converted over so they can be used moving forward in the future.
Here's another question. How do you correlate this time domain data with actual testing at an EMC test facility?
There's been a lot of work done on that in CISPR through roughly 2008 to 2010 to correlate that. First, there was a lot of work that went on actually demonstrating that, with laboratory signals, that both CW and impulsive signals captured with the time domain scan would equal give you the same amplitude value as a traditional frequency scan would. There's a lot of work that went on there to understand how much overlap in the time domain as I collect this data is going to be necessary to guarantee the amplitude accuracy that I'm talking about. CISPR has a very tight amplitude standards, plus or minus 2 dB up to a gigahertz, plus or minus 2 dB and 2.5 dB beyond that, up to 18 gigahertz, and MIL standards even tighter, plus or minus 2 dB. So the industry did a lot of work to characterize how much overlap is required to guarantee that. And then tests were done in the CISPR organization to show that you've got comparable results between time domain scans and frequency domain scans.
Great. How do I know my EUT's pulse repetition rate to determine my dwell time?
That's an excellent question. A lot of people ask that question. Some people look at the design itself. They look at elements of it. For example, we build spectrum analyzers and receivers around here. Typically, the lower PRFs we have in our boxes are due to pulse power supplies. But other manufacturers need to have other types of products that they build, so they need to look at the design of that. Another thing that some people do, they'll actually collect information from their device, either in a pre-compliance environment or in a compliance chamber, to help look for some of the pulse frequencies that come out of the device.
Great. Here's another question. Can your receivers go wider than 8 megahertz RBW in zero span?
Our designs they're nominally 8. They're more like around 10 when we have them. But for our particular devices, they're called nominally 8, but they're as wide as 10 megahertz.
Okay. Here's another question. How do I know if my EMI receiver is being impulse overloaded and needs internal or external attenuation?
There's a variety of methods that help with that. Multiple receivers in the marketplace, they have an RF overload detector in the front end of the instrument, which helps identify when the overload situation are. They don't always catch that. So other methodologies need to be used. One methodology would be to look at the signal itself and change your input attenuation by a few dB and see whether you get the same value or not, plus or minus a couple of tenths of dB. If you're heavily overloaded, as you increase your input attenuation, you'll actually see the signal amplitude increase. Another methodology would be to look at one of the lower signals that you're currently capturing. So there may be an out-of-band signal you're not currently looking at, but still within the bandwidth of the preselector. That's a very large signal that's overdriving the mixer. And you're not seeing that signal because you're not tuned to it. You're looking at a narrower signal or a lower signal that's off the main signal. You could try changing your input attenuation also there, and you'd see the amplitude of the lower signal change. So if you're seeing significant amplitude change as a function of input attenuation, then there's a good chance that you're overloaded.
Great, thank you so much. We've received so many great questions we will try to address in the future. Mark, thank you again for your time and expertise. Please join us next year for EMC Live 16, which takes place next April. Webinar attendees, if you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.